So let's have a look at hypothesis testing, specifically in the linear regression model. And in this lecture, we'll have a look at something called the t-test. So we have the following setup. I have a linear regression model and I have random sampling. And we also assume that the Gauss-Markov assumptions are satisfied. So yi is determined partly deterministically by an explanatory variable xi, and then we have an error term epsilon I, and the explanatory variable is exogenous, so that the expected value of epsilon I given xi is 0, and we also have homoscedastic errors. The variance of epsilon I given xi is sigma square and constant. So to this, we're actually going to add one more assumption, and that is we will assume that the error terms actually follow a normal distribution. So conditionally on xi, epsilon I will follow a normal distribution. It must be 0 due to the exogeneity assumption, and the variance must be constant sigma square due to homoscedasticity. So this is a simulation study that illustrates the setup. I have some X data, and econometrics is all about doing analysis conditionally on the X variable. So I don't really care what the distribution of the X data is. The distribution of the error terms are very important on the other hand. So I need to satisfy three conditions: exogeneity, homoscedasticity, and also normality. And if you look at the error terms, you can see that I do satisfy all three conditions. I simulate from the normal. I have an expected value 0, so they are exogenous. And the standard deviation for every error term is in cell B4. So 1 in this case. So they are all homoscedastic, normal, and we have exogenous X variable. I have simulated with an intercept of -4 and a slope of 2. Beta 2 is 2. So the most important hypothesis in the linear regression model is then the following. The null hypothesis is stated as follows: beta 2 is equal to 0. That's the hypothesis, and we want to use the data available to us to either reject it or to not reject it. Note first what it means. If we go back to the previous setup, beta 2 measures the effect that the x variable has on the conditional expectation of y. If beta 2 is equal to 0, it basically says that x has no effect on this conditional expectation. Thinking about a particular example, suppose that yi is the income and xi is the number of years of schooling. If beta 2 is equal to 0, it says that the number of years of schooling will not change the conditional expected income. A person with 5 years of schooling would expect to have the same salary or income as a person with 15 years of schooling if the null hypothesis is true. So that's why this type of hypotheses are so important. Lots of problems in economics are typically stated in this fashion. That is, we want to know if a particular variable either has or doesn't have an effect on the conditional expectation. This lecture will only go through the steps that you need to take in order to test this hypothesis, and it's not really going to describe exactly why it works. So here's the first step. We need to define something that we will call a t-value or a test statistic or even a t-statistic for this particular hypothesis. No matter what you call it, it is defined like this. It's defined as B2, remember that's our estimator of beta 2, divided by the standard error of B2. And remember, the standard error of B2 is square root of the estimated variance in B2. So just note a couple of things. If B2 is close to 0 or 0, then T will be close to 0 or 0. Another is that the higher the standard error of B2, the smaller is the T value, given the same value for B2. We can easily calculate the t-statistic in Excel. If I do the OLS estimation and I also request Excel to do additional statistics, then as we said, then instead of just one row, we need to highlight 5 rows. So I'll do linest for the Y data, for the X data. I have an intercept, and the important part here is I want true now. I want the additional regression statistics. End parenthesis, shift control enter, which will give us the data. And keep in mind that the first row, that's B1 and B2 in reverse order. So we have B2 and B1, just like above. And below that, we have the standard errors. So this is the standard error of B2. This is the standard error of B1. So it's very easy to calculate the t-value for the statistic. So let's type that up here, t-value. And it's simply given by B2 divided by the standard error of B2. So 24.9 in this simulation study, but if we redo it, we see we get different values for the t-value. So the t-value itself must be viewed as a random variable. And here is the basic idea behind the hypothesis. I want to test if beta 2 is 0 or not. Well, let's see what happens if beta 2 is 0. If beta 2 actually is 0, then the OLS estimator B2, being unbiased, will be pretty close to 0. So when I calculate the t-value, that too will be close to 0 by just F9ing this, because it's B2 divided by something. And if B2 is close to 0, the t-value will be close to 0. However, if beta 2 is not 0, like when it's 2, then the t-value will be further from 0, as we can see here. Similarly, if the true beta 2 is minus 2, then since we are doing B2, since we're doing the t-value as B2 over standard error, and B2 will in this case be close to minus 2, this will be negative but far from 0. And that's the idea behind the test. If I look at this t-value and I see that this t-value is far from 0 in absolute terms, then probably beta 2 is not 0. If I, on the other hand, see a t-value which is fairly close to 0, then it is possible that beta 2 was 0. So we need to formalize this technically so that we can actually calculate the level of significance and determine when to reject the null hypothesis. So you can actually show, and we're not going to prove that in this lecture, that if the null hypothesis is true, if beta 2 actually is indeed 0, this t-value will follow a t-distribution with n-2 degrees of freedom. But that is under the null, if the null is true. Remember, we talked about how we can simulate random numbers from the t-distribution with the determined number of degrees of freedom. So the fact is that if I set this to 0, now focus on this cell here in B20, whenever I F9, you can view that as a drawing from the t-distribution with, well, n is 20, so n minus 2 is 18. So we can view it as a drawing from the t-distribution with 18 degrees of freedom. So let's just state that if the null hypothesis is true, the t-statistics follow a t-distribution. So this has a probability density like this, symmetric around 0, expected value 0, and so on. Just like we talked about in the introduction to hypothesis testing, if I now actually get a t-value which is way out in the tails of this distribution, then I should probably say that that is not correct. This is not drawn from a t-distribution with n minus 2 degrees of freedom. Well, if you are saying that does not come from the t-distribution with n minus 2 degrees of freedom, then you're also saying that the null hypothesis must be false. That is, then you have to claim that beta 2 is not 0. So the question then is just, when should we make the cutoff? When should we say that we reject the null simply because the t-value is too far from 0? Well, that's when the level of significance comes into play. So if we decide on a level of significance alpha, remember that's the probability of incorrectly rejecting the null. If we decide that to be, let's say, 5%, then we are done, because then all we have to do is to find this value and this value such that the area of the tails is in total 5%, 2.5 here and 2.5 here. Well, we know exactly what that cutoff point is. Those are called the critical value for the t-distribution. So this particular value is denoted by t alpha half, because this is half of alpha, and n minus 2 degrees of freedom. We can easily calculate this number. Just look it up in a table, for example, or use Excel or any other software. If our t-statistic ends up beyond that value, out here in the tail, then we can simply claim that it's unlikely that this comes from this t-distribution. And even better, if we use this particular cutoff point, this critical value, then the level of significance for our test will be precisely alpha. We'll make the mistake of incorrectly rejecting the null 5% of the times, just the way we want it. So to summarize the next step, so what we need to do now is we have to decide on an alpha, and in econometrics the most common value is 5%, but there are cases when you need a different value. So we decide on a level of significance, and then we simply reject the null hypothesis whenever we are out in the tails of the t-distribution. That is, when the absolute value of the t-statistic is greater than the critical value. So when the absolute value of the t-statistic is greater than the critical value, then we are out in the tails, and we should say that this probably doesn't come from a t-distribution, and then that then means that beta 2 was not 0. So let's find the critical value for this particular setup, and let's do that with alpha equal to 5%. Then the critical value, t critical, is, we talked about in previous lectures, you can get that from t dot imb dot, if you do two tails, you don't have to half this 5% yourself. You can just do the alpha and the degrees of freedom. Remember, n minus 2, so 18 is the degrees of freedom. So this is the critical value. So let's just type reject here, And in this cell, I want Excel to write either yes or no, depending on whether we should reject. And you can actually make Excel to take these yes/no decisions by using the if function. So if you do if, and you remember that we should reject it if the absolute t-value was greater than the critical value, we can do abs, which just takes away the negative sign, t-value greater than the critical value. If this is true, it says, comma, put value if true. So I'm just going to typing then, yes, reject the null. And the value if false, I'm just going to type no, don't reject it. So here it writes yes. In this case, we will actually reject the null hypothesis. So this first simulation of yes actually came out to be an incorrect decision. This is the wrong decision because beta 2 is 0 and we are rejecting it. But remember, mistakes happen when we do hypothesis testing. The only thing is that it only happens in 5% of the cases with the 5% probability, if you like. So if I F9 this, then approximately 1 out of 20 times I will get the incorrect answer, yes. No, 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 no. Yes, no, 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 no. Try it yourself. You can see that you will get no approximately 1 out of 20. However, if I change this beta 2 to 2, now the null hypothesis will no longer be true and we want the reject to say yes. And if you look at it, it's actually going to say yes pretty much every time. Yes, 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 yes. And the reason is, of course, that our B2, which will have an expected value of 2, will be far from 0. The t-value will be far from 0. And it will, in almost all cases, be greater than the critical value, 2.1. So this value, so re-emphasize that, is not drawn from the t-distribution. It's only drawn from a t-distribution under the null, that is when the null is true. So don't worry too much if you don't understand all the technical details behind this test. Just make sure that you are able to perform the test because it's something that we do a lot in econometrics. So here I have another data set which is actually a real data set. Final is the result of a final exam, and let's just use SAT-M, that's the result on the SAT for the math section. And we want to run a regression explaining the final exam using only the result of the math section of SAT. So let's do that. 2, 5, linest, y variable, that's my final, comma, the x variable is the SAT-M, intercept, statistics, shift, control, enter. So that's it. Reverse order, so this is B2, this is B1. So this 0.05 should be interpreted as the increase in the expected result on the final exam if the student had 1 point more on the SAT-M. So 10 points more on the SAT results in about half a point more on the final exam. The R-square is only about 14%, so the SAT score for math doesn't explain final result all that well. So let's say I want to test if beta 2 is 0. Again, that means that the SAT-M has no effect at all on the expected final result. To do that, we again remember calculate the t-value, and that was just simply the b2 over the standard error of b2. That's the t-value. We calculate the critical t-value or the critical value, and if I use 5% again, it's t dot imb. I need to find the number of observations first, so that would be 99. Let's go back. T dot imb dot two tails 5%, and 99 minus 2 is 97. So the critical value will be this, very close to the one that we get from the normal distribution, which is 1.96. And you can clearly see that since this is greater than that, we should reject the null hypothesis that beta 2 is 0. We say that beta 2 is statistically significant, or sometimes we say it's statistically significant different from 0. Sorry, I meant B2. We say that B2 is statistically significant. We say that B2 is statistically significantly different from 0, or sometimes we just say that B2 is statistically significant. So even though B2 looks like a small number, 0.005, it is not 0. It's different from 0 with the level of significance at least 5%. There is another way you can do this type of regression analysis in Excel without using the linest function, which I think is a little bit more useful. And that is if you first include the add-in, which is called the data analysis. So just go to File, Options, and here in the add-ins, down here, Manage Go, just include that add-in. Then what you can do is you go to Data, you just click on this, Data Analysis, and this has something called Regression. Click OK, and then you have to tell Excel your Y and X range. So my Y range, if I click this button, is, I think I can even include the title. So like that. My X range is then the SAT-M. Okay, then I can do, for example, if I want the intercept to be 0, I can click that one. I don't want that. I want the result on a new sheet. Let's call it OLS. And you can get some other stuff as well. You can get the residuals if you want that, plot of the residuals, and some other stuff. Let's just get this. Okay, so my mistake, don't include the title of the variable. So let's change the 1 here to 2. This was irritating. Like this, so it goes from A2 to A100, 100, and C2 to C100. Like this. Then you get a printout which looks sort of similar to the printout that you get from eViews or Gretel or Stata or any other econometric software. You get the estimated coefficients right here. So that's the intercept, that's for the x variable, that's our B2. You get the standard errors a little bit more nicely. You can see exactly where they are, but of course they are precisely the same numbers as here, but it's easier to see what they mean. And the Excel also calculates the t-statistic, 4.038. Let's check that. That's what we got as well. 4.383. It does not give you the critical value. It gives you something else, which we'll talk about in a second, which is equally nice, namely the p-value. But since we have so many observations, the critical value is close to 2 or 196, so it's pretty clear that we should reject the null hypothesis. The reason, of course, it doesn't print the critical value is that it depends on the level of significance. And Excel or any econometric software doesn't know which level of significance you want to use. So let's then have a look at this p-value that Excel also prints for us, because that's typically the number that you actually look at. That's the probably this number right here is typically the most important number of them all in this printout. So here's the discussion and the definition of the p-value. So the hypothesis we're looking at is beta 2 equal to 0. This hypothesis allows us to define a p-value, and the p-value is the level of significance such that we are precisely indifferent between rejection and not rejecting the null. So as you can see in this printout, the p-value is something like 0.000107. If someone weirdly said, I want to test this hypothesis and I want the level of significance to be 0.000107.6 and so on, it would be an incredibly weird level of significance, I admit, but if that was the case, then the result would be to be indifferent. That is, we can neither reject it nor not reject it, or you can do both if you like. We're just right on the cusp here. And that's what the p-value is. But that's not the importance of the p-value. The importance comes from this discussion. If I pick precisely this number as my level of significance, then this t-statistics is exactly also the critical value. So that's why I'm indifferent. But we know that there is an inverse relationship between alpha and the critical value. So if I increase alpha, the critical value will go down and I will end up rejecting the null. Let me say that again. If I increase alpha, critical value goes down because the tail gets bigger. The t-statistic stays the same, so I will end up rejecting the null. In particularly, if I increase this all the way up to 5%, then the critical value will go down from 4.03 and I will end up rejecting it. And that's the way we use it. All I need to do is to look at this p-value. I see that the p-value is less than 5%. Since it's less than 5%, I know that I can reject my null hypothesis. It's nice because I don't have to look up the critical value. So look at the p-value. If it's less than your level of significance, say 5%, reject the null. If it's greater than your level of significance, do not reject the null. That's the rule that we use. So some theory about that. The level of the p-value is where we are precisely indifferent. That is, when the t-statistic is exactly equal to the critical value. So you can see I put a p here as my level of significance. And like we said, if the p-value is less than alpha, the p-value is less than 5%, let's say, reject the null. If the p-value is greater than alpha, do not reject the null. There is a famous way of remembering this, because it is something we do a lot and it's something that you need to remember. And the saying goes something like this: if p is low, the null must go. If p is high, the null will fly. If you remember this sentence, you remember where to go. if the p-value is low, and low is then in reference to your alpha, 5%, then the null must go. That is, then you need to reject it. A low p-value is always connected with rejection. If p is high, then the null must fly, or then the null will fly, meaning that the null is fine now. The p-value is high, don't reject the null. Here clearly the p is low, the null must go. If you look at the intercept, because we can do exactly the same thing for the intercept. If I consider the null hypothesis that beta 1 is equal to 0, then the p is high. It's higher than 5%. So the null must fly. That is, you can't reject that null hypothesis. It's very possible that the intercept is 0. And based on that, something really important, it's not the size of the coefficient that matters. So even though this number is way, way above 0, it's not significantly higher than 0. It could just be a random thing that we get something that's bigger than 0. While this number is close to 0, but it's still significantly different from 0. We have much better precision in that estimate, and you can see that from the standard error. The precision in this guy is a lot higher than the precision in that guy. So let's see how to do the same thing in Gretel. Then I have the same data imported. Just go to model, ordinary least squares to estimate the parameters first of all. Final, sat them, OK, gives you this result. And now you have the t-statistic there. You have the p-value right there. So this is low, the null must go. Gretel also helps you with these little stars. I think 3 stars is when the p-value is below 1% or something like that. Evalues, just do finish, no. And you do quick estimate equation. You do final, C, SATM. OK, gives you this. And now you have the t-statistic right there and the p-value right there. So in this lecture, we focused fully on this hypothesis, beta 2 equal to 0, which we said was the most important hypothesis. But you can actually test other types of hypotheses. So you could test an hypothesis such as this one, beta 2 is equal to 0.05, for example. You don't have to have an exactly 0 on the right-hand side. However, testing such an hypothesis is a little bit trickier because you cannot just look at this printout. You have to perform this test manually. In eViews, you would perform this by going to View, Coefficient Diagnostics, and Coefficient Restrictions, the wall test. And then you would simply type in the restriction you want to test. So if you look at the example, C parenthesis 1, that refers to the first coefficient in the list. So SATM would be the second one. So if I want to test if beta 2 is 0.05, I would type C of 2, because that's the second one, equal to 0.05. Do an OK, and then we can look at the same thing, the t-statistic, and probability here is the p-value. So this p-value is high, the null must fly. We cannot reject that one, so this is not rejected. Which kind of makes sense, right? Because B2 was pretty close to 0.05, so that's not rejected. If you want to perform the same test in Gretel, you can go to Test, Linear Restrictions, and type this, B, square parentheses, and then the name of the variable, which was SATM, equal to 0.05, and you get the p-value right there. Gretel doesn't report the t-value in this case, only the f-value, which is for the case when you have a 1 here, the f-value is just the square of the t-value. Compared to eViews, it's this number only that's reported by Gretel, and it's exactly the square of that one. This type of hypothesis is more difficult to test in Excel. Then you have to do more manual work. And it just goes to show that Excel really isn't an econometrics software. But because of this feature of updating cells when we change something in one cell, it's an excellent pedagogical tool. Plus, you can do basic. So the final thing I want to say about hypothesis testing in this linear regression model is to discuss one of the assumptions that we made. So technically, everything that we have said is only true if the error terms follow a normal distribution. So in a real world setting such as this one, when we try to explain the final with the result of the SAT score, it's just really hard to know that the errors follow a normal distribution. But fortunately, we can add a little bit to this, and that's the following. If n is large, n is the number of observations, then we can say the following. If the Gauss-Markov assumptions are satisfied, so we have exogeneity and homoscedastic errors, but the errors do not follow a normal distribution, then the t-statistic will actually converge to a standard normal distribution as n goes to infinity. You need some additional very mild conditions which are typically almost always satisfied. And this is very good news for us. It follows by a theorem or a result known as the central limit theorem. Because what this means in practice is that even when the errors are not normal, our t-statistic is very close to following a t-distribution. So everything we have said so far is almost correct. The level of significance might not be precisely 5%, but it will be very close to 5%. So how large is large? Well, that kind of depends a little bit on the setting. But in most cases, if you go like above 30 or so, then you probably don't have to worry too much about this normality assumption. So keep this in mind. If n is large, then everything works as long as we have the Gauss-Markov assumptions. Without those, then the whole thing will definitely fall apart, but the normality assumption is not so important.